Sorry guys, again, a lot of interruptions. So really, if I care that you know about these semiconductors, the only thing that I'm going to ask you about is what is a semiconductor, and you would tell me that a semiconductor is just a material that has an electrical conductivity. It can act like a conductor, but it's going to be in between a conductor and an insulator. So it has some type of electron movement. It's not going to be anywhere near as great as a conductor, but it's going to be a lot better than an insulator. Which family on the periodic table act like semiconductors? You would tell me that that would be group 4A, which is that carbon family. And really, why do they do it? It's because they have that ability to gain and lose electrons very readily. So it doesn't matter whether they gain, doesn't matter whether they lose, but because they have that option to constantly move their electrons, that's what makes them at least conductive. And if I asked you to explain on more of a particulate level, so like what's happening in terms of their electrons, I would want you to go to the molecular orbital theory, and I would want you to tell me that semiconductors can be based on a couple different things. So what makes a semiconductor on the particulate level is that their valence band, meaning their bonding molecular orbitals, are close to being full, if not full. And their conduction band, the anti-bonding modes, are completely unoccupied. Because of that, there is an integrity and a strength, a good strength, within their bonds. So they're very stable, and they're able then to have that semiconductive property. The other thing that I want you to know with the molecular orbital theory or molecular orbital diagram is that as this energy gap between bonding and anti-bonding orbitals gets bigger, or as it's larger, then that means it will be a better semiconductor. And that's just really has to do with the size of the actual atoms. So as you move down that 4A column, as I go down that carbon family, carbon and silicon are really great in terms of their semiconductive properties. But as I get to tin and lead, they don't really act like semiconductors at all because their atomic radii are so large that I have a lot of shielding, less coulombic attraction. It's just too much for this gap to really even exist. So in lead, we actually don't even see a gap here. So band gap is important, valence band, conduction band is important. Okay. One way that we can utilize semiconductors, or a way that we have at least utilized them in terms of technology, is creating something through the process of doping. Adding impurities to different types of semiconducting material, it helps us try to increase the number of charge that it can carry. So if I increase impurities, I could have more electron flow, which then would make the conductor even better. So this process is just called doping. And doping is just adding impurities to a semiconductor, okay? What happens when we add a dopant to replace atoms in a crystal? So if I add an impurity, we're going to call that a dopant. There's two different types of doping. There's an N-type semiconductor, and then there's a P-type semiconductor. And you'll see that these have to deal with the MOS. This has to deal with the molecular orbital theory. So what I want you to see here is that the blue is going to represent my valence band. And the valence band are those bonding orbitals. And again, they're lower in energy. It should make sense that they're down here. And then my pinkish kind of color, peachy-ish kind of color, is representing those anti-bonding orbitals. And again, we called that, remember, the conduction band. In an undoped semiconductor, we're going to see that I have a filled molecular orbital and an empty conduction band, so an empty anti-bonding molecular orbital. As soon as if I talk about the N-type semiconductor, really what's different between N-type and P-type? Well, an N-type semiconductor adds extra electrons, so we force extra electrons to occupy our conduction band. I'm adding extra electrons then into those anti-bonding orbitals. So ultimately, all this is doing is starting to give me more electrons So then that way I can increase that conduction band. And when we do that, we see that if we add just a very small number of electrons, then it can actually increase, depending on whatever element we're talking about, it can increase its electrical conductivity just because of the presence of those impurities, just because of the presence of some extra electrons. P-type is going to be the opposite, in which I'm going to actually take away some electrons from that bonding molecular orbital. So there are what we would call electron vacancies in that filled molecular orbital, or what we would say is the valence band. All we're doing in the p-type is replacing an original atom with an atom that has less valence electrons. So in the n-type, I'm going to add an atom that maybe has more than 4 valence electrons. And in the p-type, I'm going to add an atom that doesn't have 4 necessarily. It's going to have just a little bit less valence electrons. So I'm not necessarily filling all of that p-type valence band. What I want you to care, or what I care about you knowing for doping, is just what it means. So doping is just adding very small impurities to a semiconductor, so that way we can increase the conductivity of that semiconductor. And I want you to know that we can do it in 2 ways. So I can do it by adding an atom that has a little bit more valence electrons. So now I'm filling just a couple electrons in that anti-bonding molecular orbital. And when we experimentally, when we have done that, we have seen that it can increase the conductivity of a semiconductor. Does that work in every case? Absolutely not. It will totally depend on what atoms you're talking about. So doping isn't a process that works. Doping isn't a process that works every time based on every single atom or element. It's going to depend on what we're doping. And then the p-type is that second type, and p-type is going to be where I'm adding an impurity or replacing something, replacing an atom that has fewer valence electrons than what it had originally. And so that is going to leave the conduction band still unoccupied, but it's going to leave me also with a not completely filled valence band or bonding molecular orbital, okay? So now moving over to polymers. Polymers are just molecules of a very high molecular mass. And polymers are going to have a pattern to them. They're going to have a repeating unit. And that repeating unit is going to be called a monomer. So they're just really long chains of atoms. And these polymers are also going to be connected by covalent bonds. It's really important that we know that polymers are covalently bonded together. And they're going to have those adjacent chains, and they're all of the adjacent chains. So if I stack all of these, for example, we took ethylene and we bonded all of the ethylene together. So I took these monomers, bonded them together to make polyethylene. If I had a stack of all of these polyethylene molecules, then we know that they're going to be largely held together through intermolecular forces, and specifically with this one, if I'm talking about just all these carbon-hydrogen chains, it's going to be those London dispersion forces. Polymers are normally stronger and have higher melting points than molecular solids will, and that's really just because they're these really long carbon-hydrogen chains where intermolecular forces holding them together are going to be really, really strong. Those dispersion forces, because they're long, skinny chains, are great. Yes, thank you. Okay, another last thing about polymers is that they are very, very flexible. So when we take these 3 ethylene molecules like we have here, we're going to end up breaking this carbon-carbon double bond. And I'm seeing that I'm going to break that in all 3 of these to then create a carbon-carbon single bond here with hydrogens then coming off all of those the long carbon chains. This process is called polymerization, where I'm taking a repeating unit, a monomer, I break whatever that central bond is to try to link them all together. So polymerization is just the joining of those polymers. In your book, table 12.5 is just an example of different types of polymers that we have. There's polyethylene, polypropylene, there's nylon, if we're looking at that here, polyurethane. So a lot of these things are just made for packaging and insulation, any type of like gladware, kitchenware. That stuff is going to be made from some type of commercially manufactured polymer. if we look at this one down here, I really like this one. So polycarbonate is what your eyeglass lenses are made out of. CDs are made out of it. Bulletproof windows are made out of polycarbonate. So if you just want to go through this list, I'm not going to ask you specifically about any of these. They'll give you the structure and they'll give you the name of them on your AP test. I just think some of them are kind of cool to see what their uses are. The way that we can get polymers is in a couple different ways. So there's addition polymers, and then there's also something called condensation polymers. So an addition polymers are made by coupling the monomers, and we're ultimately just converting pi bonds within each monomer to sigma bonds. So remember that a pi bond is only present when I have a double bond or a triple bond. So in addition polymers, what we're going to do is we're going to break a carbon-carbon double bond, and we're going to make it into a carbon-carbon single bond. So that's what an addition polymer is. So what will happen is, as I break that pi bond in this carbon-carbon double bond, it's going to leave open then a pair of electrons. So because of that, this one single carbon-carbon bond can come and link to another one that I've just broken, and that's what's going to create that carbon-carbon single bond, okay? Condensation polymers are a little bit different, and that condensation polymers are made by joining two subunits and trying to get rid of another unit that was originally connected to those subunits. A lot of times in condensation polymers, you're going to have a byproduct of water. So for example, let's say that I want to link two monomers here together. Because there's an OH group here and there's another H attached to the nitrogen here, if I take this water off, I can connect the carbon and nitrogen bond here with a single bond, and then I can get rid of water. So this is just what's called a condensation polymer. I'm connecting two subunits by getting rid of usually it's water, by getting rid of a molecule, and then I can create a polymer. Okay, so synthesis of nylon. I'm actually not going to go through this because I know that this is not on your test. Yay, I know. So I'm adding polymers on here because you're going to see something about polymers maybe somewhere on your test. They will give you all structural formulas. They will give you the chemical formula. They will tell you that it's a polymer. I think that the only thing that you need to really know about polymers are the fact that you can have two different ones. There are two different types. We have an addition polymer here, which is just made by breaking a carbon-carbon double bond and forming carbon-carbon single bonds here. Okay, so I'm converting a pi bond into a sigma bond. The other type is a condensation polymer, which is really where I can connect two monomers by just getting rid of something that's at the end of each of those monomers. So in most of the cases, it's going to be water. And again, I can see that that's just going to be singly bonded there. So different properties of polymers. Interactions between chains of a polymer lend elements of order to the structure of a polymer. So what does that mean? Polymers have a lot of strength to the fact that even though they're not an ionic solid and even though they're covalently bonded, because we're constantly just linking a repeating unit over and over again, because of that constant unit, because we're repeating that, it gives us some type of structure for that. So because we have that repeating unit, because we have some type of pattern, because we have some type of organization, it will at least yield to the strength of it. And atoms in a polymer are also pretty relatively free to rotate around the carbon-carbon single bond. So if I go back to look at this one, these hydrogens are able to just kind of move around just because these are singly bonded. So I have some ability to have a little bit of rotation there. Polymers can kind of soften. Another property of them is that they can soften over a range of temperatures. And we usually think about polymers to be more in the category of like the amorphous solids. So they're definitely not crystalline in terms of their solids. They have their order, we already talked about that. And we already talked about how their IMFs holding them together are those intermolecular forces, London dispersion forces, and they're actually quite strong just because polymers have those long skinny chains and there's a lot of surface area for those intermolecular forces to happen. Okay, if we stretch the polymer chain, stretching the polymer chains as they form can increase the amount of order, leading to a degree of crystallinity of the polymer. What that means is that as I continue to add more and more monomers to that overall polymer, I'm increasing the amount of order that it has. And as I'm increasing that amount of order, I'm also lengthening that polymer, which is also allowing for more intermolecular forces like London dispersion forces to occur. So it really just kind of helps solidify the strength of a polymer. Using polymers, we can have something called cross-linking, and chemically bonding chains of polymers to each other is what cross-linking is. So if each of these little red bonds here is just where these polymers have been cross-linked. And whenever we cross-link, we actually stiffen what that polymer chain looks like, and it will strengthen that substance. So I've kind of forced those polymers to be even closer to one another, and I'm inhibiting more of their movement. So they have to have more of that intermolecular attraction holding them together. So the greater the number of cross-links, the more rigid that polymer is going to be. So things that are those like thermosetting plastics. So any type of like thermos or any type of kitchenware that you can actually put in the microwave and heat up, those would have lots of polymers that are cross-linked because they're much more rigid, and then it helps them hold their shape. So we cross-link to try to get those properties that we wanted there. Some cross-linking can happen just naturally. Rubber, naturally occurring rubber is very, very soft. And so we have added extra cross-linking with it, so then that way it can be used for more applications for our needs. So that's just another example. Vulcanization is where chains are cross-linked by short chains of sulfur atoms. So cross-linking is really just trying to bridge two of these polymers, or two or more, or however many of these polymers together. But in vulcanization, we're actually just adding sulfur atoms to cross-link them. And whenever we do that, it just, again, makes it stronger. And then sulfur atoms, when we try to break that cross-link, it's actually really hard to break the bond with sulfur atoms, so it just makes it less susceptible for breaking. Also makes it less susceptible for what it says down here, degradation. Nanoparticles is this very last piece of our chapter 12. And nanoparticles is something that has been huge in the last at least 10 years. So different size particles of semiconductors. They can emit different wavelengths of light depending on that band gap, depending on energy. And nanoparticles have really made Dalton's four postulates kind of stand out to us in most recent history a lot more. Dalton in his four postulates said that atoms of the same element will act like themselves. They will act like that same element. We know that to be false now, and we know that to be false because of nanoparticles. When we have isolated an individual atom of iron, which is what we would call to be a nanoparticle, it acts totally different than how the rest of those iron atoms will act when they're all grouped together. So for us, we are using these nanoparticles in the medical industry, in that we're trying to use them in that they'll target cancer clusters. We're also using a lot of nanoparticles in computer chips, in different pieces of technology, and for us it's working right now. We have something that's also called a quantum dot. I can allude to that a little bit more tomorrow if you want to, but we've been going for a little bit, so I feel bad that this video is super long. I know. So finally with our nanoparticles, we're not able to fully describe why nanoparticles act the way that they do. Why is it that when I take one single iron atom or one single gold atom or silver atom away from that overall element, why does it act differently than the group of them together? And that's really what our focus has been currently on nanoparticles. So far, we've just observed that they act very differently, and we're using it to our advantage. We need to figure out why they're acting differently, though. So maybe that's what your research can be after your little AP Chemist, because you are AP Chemist. Oh my gosh, makes me so happy. Okay. I know. Carbon nanotubes. So a carbon nanotube is ultimately just a bunch of carbons together that are in a tube-like shape. Guess what? That's pretty straightforward. Carbon nanotubes are actually, they will hold a lot of semiconducting properties, and they do that without the process of doping. So I don't need to have any additional impurities added to them. We have utilized carbon nanotubes in the cancer industry. It is huge. So carbon nanotubes have been implemented to try to target specific cancer cells, and they have been widely successful. The only problem is that making these carbon nanotubes is a really long and tedious process, so it's really difficult to make them. So because of just their rarity, they are very expensive. So if we can get to a process of making the carbon nanotubes the way that we want them at a cheaper cost, then I think that they would be more widely available to us. Okay, tomorrow in class, we're gonna look at some real-world applications of those intermolecular forces, and I have some pictures that I wanna show you with that, and then we can actually look at some different carbon chains on this first video here. I'll post this PowerPoint so that way you have these notes, and then our goal is to try to get through as much of the notes as we can tomorrow. Go through that worksheet that you had on the types of the strongest type of intermolecular force. And then hopefully Thursday we can do Christmas chemistry carols. And then on Friday and Monday, we'll study, review for your test, as well as do some practice FRQ multiple choice. Okay? Have a really great night, guys. Bye.